The flight control system of the Q400 includes roll control, yaw control, pitch control, and the wing flap system. Roll control is provided by ailerons, which are controlled by cables, and two hydraulically actuated roll spoilers on each wing that support the upgoing aileron. The ailerons are controlled by the co-pilot control wheel, the roll spoilers by the pilot control wheel. The two circuits are normally interconnected, but if either system jams, they can be separated. Geared tabs provide aerodynamic assistance. An aileron trim unit provides aileron trim of the aileron control surfaces. Gust protection for the ailerons is supplied by a gust lock mechanism operated from the flight compartment, which locks the ailerons in neutral position. The yaw is controlled by the rudder. The rudder pedals actuate two hydraulic cylinders via a single cable circuit. Artificial feel is provided by springs. There is a fore and a trailing rudder. The actuators move the fore rudder directly, while the trailing rudder is linked geometrically to double the movement of the fore rudder. Rudder trim is provided by an electrical actuator. If the system is without pressure, a rudder hydraulic damper maintains rudder position against wind gusts. Pitch control is provided by the left and right elevators. They are independent, mechanically controlled, and hydraulically operated by the pilot's and co-pilot's control column. The two circuits are normally interconnected. If jamming occurs, they can be separated. Elevator trim is performed by the autopilot or manually by the trim switches on the pilot's and co-pilot's control handwheels. The wing flap system consists of two segments on each wing. The flap selector transfers the input via a signal to the flap power unit. The flap power unit is powered by the number 1 hydraulic system. It operates the flaps via a flap drive system. Flap settings of 5, 10, 15, and 35 degrees are available on the Q400. The following powered flight control surfaces position information is available in the Permanent Systems Data area of the MFD number 1 when the nav or the system page is selected. The elevator position, the rudder position, and the spoiler position indication. On MFD number 2, the flap angle position is indicated. On the trim control panel, the aileron and rudder trim indicators show trim position of the flight controls. Caution lights provide indication of flight control malfunctions, while advisory lights indicate system operation. The Flight Control Electronic Control Unit is a single unit divided into channels 1 and 2, which receive inputs from the pilot and or co-pilot flight control commands and from individual flight control system components. The unit processes the signals and sends to the individual flight control systems like the aileron control system, the elevator control system, the rudder control system, the spoiler control system, the flap control system, or the flight control indication system. Roll control is provided by two ailerons assisted by two flight spoilers that are independent systems. Both systems are mechanically connected to allow simultaneous operation for normal roll control. The co-pilot control wheel operates the ailerons mechanically through the cable circuit. Rotary movement of the control wheel is transmitted using a sprocket and chain mechanism to the base of the control column. A lever transmits the movement via a push rod to the aileron quadrant underneath the flight compartment floor. The aileron autopilot is also connected to this quadrant. The aileron quadrant transmits the input to the aileron splitter quadrant. A geared tap is hinged on both aileron trailing edges. The tap is connected to the aileron by 4 hinge fittings and a geared linkage. At full aileron deflection of 17 degrees, the geared tap deflects 11.9 degrees out of the airflow to reduce pilot effort. As the aileron returns to neutral, the tab is geared to neutral. The aileron trim and centering unit provide aileron trim and automatic centering of the aileron control surfaces. The unit is connected to the aileron trim actuator and the aileron forward quadrant. Rotating the control hand wheel turns the forward quadrant. When the input to the hand wheel is released, the hand wheels return to the neutral position in zero trim condition. The aileron trim switch has 3 positions and controls the trim actuator. The switch is spring-loaded and returns to the center off position. The aileron trim and centering unit transfers input commands from the aileron trim actuator to the aileron forward quadrant. The forward quadrant rotates and transfers the trim commands to both aileron control surfaces. Therefore, aileron trim is accomplished by deflecting both aileron control surfaces. The neutral position of the control wheel is also repositioned. The amount of trim is shown on the aileron trim indicator of the center console. When the autopilot is engaged and aileron trim is required, mistrim, trim left wing down, or mistrim, trim right wing down, is shown on the primary flight display, PFD. The autopilot must be disengaged, and the pilot then sets the required aileron trim with the aileron trim switch until the control forces are removed from the hand wheel. Rotary movement of the co-pilot's control hand wheel is transmitted by a sprocket, chain mechanism, and lever assembly to the aileron forward quadrant below the flight compartment floor. The sprocket and lever assembly at the base of the co-pilot's control column has a clutch that is used for roll disconnect purposes. A roll disconnect, roll disc handle, located at the forward center console operates the clutch. The aileron trim and centering unit and the autopilot servo are also connected to the aileron forward quadrant. Aileron control cables are routed aft from the aileron forward quadrant, up the forward face of the flight compartment bulkhead, and aft along the cabin roof. The cables then pass through pressure seals in the cabin roof to terminate at the aileron splitter quadrant on the aft face of the wing rear spar. The quadrant has 3 pulleys installed on a common shaft. One is used for the input from the control column, and there is one for each aileron output. Gust locking of the ailerons is supplied by an internal spring-loaded lever. When the gust lock is engaged, a plunger is inserted in the gust lock plate at the base of the splitter quadrant, locking the ailerons in neutral. Left and right aileron control wing cables are routed outboard from the aileron splitter quadrant, 1 cable along each wing. Each aileron control wing cable then terminates at an aileron terminal quadrant located on the aft face of the wing rear spar. Aileron terminal quadrant movement is transmitted to the aileron by a push rod. The aileron trim and centering system consists of the following components: the trim actuator, the centering unit, and the ground adjustable trim tab. Aileron trim is achieved by electrically trimming both aileron surfaces through the actuator located in the aileron trim and centering unit. The pilot controls the amount of aileron trim by operating the aileron trim switch, which supplies the electrical signal to the aileron trim actuator. Selection of the LWD, left wing down position, extends the aileron trim actuator and turns the aileron forward quadrant, causing both aileron surfaces to move differentially. Selection of the RWD, right wing down position, reverses the process, causing the ailerons to move in the opposite direction. An aileron trim indicator, located on the trim panel in the center console, shows aileron trim position. The aileron trim indicator receives its information from a linear variable differential transformer, LVDT, which is located inside the aileron trim actuator. The LVDT also transmits aileron trim position data to the flight data recorder. The trim and centering unit is connected to the aileron forward quadrant by a spring torsion bar that makes sure the aileron surfaces always return to a neutral position. It has a spring torsion bar that links the aileron trim actuator to the forward quadrant. An input to the control hand wheel turns the forward quadrant, which displaces the aileron surfaces. A torsional load is applied on the spring torsion bar. When the input to the hand wheel is released, the load on the torsion bar causes the control hand wheel to return to a neutral position. This control hand wheel centering action reduces the workload of the pilot or co-pilot. A ground adjustable trim tab is located on the trailing edge of the right aileron, inboard of the geared tab. The tab is used to adjust for any aerodynamic asymmetry between the left and right ailerons due to manufacturing tolerances. The trim tab is adjusted by maintenance personnel after a flight test and only as required thereafter. There are two aileron control surfaces installed on the outboard end of the left and right wings. Each aileron is attached to the trailing edge of its related wing by 4 hinge fittings. A horn with internal mass balance weights is located on the outboard end of each aileron to give aerodynamic balance. Each aileron has a geared tab, which gives aerodynamic assistance to the aileron control surface. The aileron geared tabs are attached by 4 hinge fittings to the trailing edge of each aileron. The tab geared linkage is connected to the aileron hinge point to give controlled tab movement in proportion to aileron movement. Only the right aileron has a ground adjustable trim tab located inboard of the geared tab. The aileron and roll spoiler control systems are normally interconnected by an interconnect rod, which provides a synchronized movement of the two systems. In the event of jamming of either system, they can be separated by the roll disconnect system. A clutch mechanism on the bottom of the co-pilot's control column is normally engaged. To disengage the clutch, the roll disconnect handle must be pulled and then rotated 90 degrees to remain in the disengaged position. This will separate the push rod attached to the pilot's control column. The control columns can now be moved separately and the jam system identified. When the handle is rotated 90 degrees and released, it will be pushed in by the return spring. The clutch will be forced in by the engagement spring when the control columns are in the same position. The spoiler 1 and spoiler 2 switch lights are located on the center glare shield panel. When the roll disconnect handle is pulled, a micro switch is closed by the roll disconnect lever assembly. If the co-pilot control handwheel is rotated more than 50 degrees to overcome the effects of a jammed spoiler control system, the aileron quadrant also closes a micro switch. The spoiler 1 and spoiler 2 switch lights come on, indicating a jammed spoiler. Pushing the 2 switch lights depressurizes the spoiler PCUs, allowing the jammed spoiler panels to retract flush with the wing surface. Directional control for the aircraft is achieved using a 2-piece rudder. The sections are designated as fore-rudder and trailing rudder. The fore-rudder is actuated by 2 hydraulic actuators mounted in the vertical stabilizer. Push rods from the fore-rudder transmit the movement to the trailing rudder. The push rods are geometrically arranged so that the movement of the fore-rudder is copied by the trailing rudder. The movement of the rudder is controlled from the pilot's and co-pilot's rudder pedals. 1 cable circuit from each side is routed back through the underfloor compartment. At the rudder mixing quadrant, the movement of the 2 circuits is transmitted to 1 cable. This cable circuit is routed back through the left underfloor compartment to the tail. In the vertical stabilizer, the cable is routed upwards to the pulley quadrant. A push rod connects the quadrant to the actuator unit. On the co-pilot's input quadrant, there is a rudder input restrictor. At a flap setting of 0 degrees, a plunger is engaged between 2 restrictor stops on the input quadrant. This limits fore-rudder deflection to 12 degrees in either direction. Selecting the flaps to 5 degrees or greater disengages the plunger. This allows a maximum deflection of the fore-rudder 18 degrees left or right of center position. Movement of the rudder pedals supplies yaw commands to the rudder control system and is mechanically transmitted from the pilot's and co-pilot's rudder pedals via the rudder feel and trim unit. This gives artificial feel to the rudder pedals during operation and also the rudder power control units to the rudder surfaces. The power control units move the rudder surfaces by using hydraulic power. Power control unit number 1 receives hydraulic power from the number 1 system, and power control unit number 2 receives hydraulic power from the number 2 system. Hydraulic pressure supplied to both power control units is regulated by the flight control electronic control unit as airspeeds vary to reduce excessive yaw rate. This means that when the airspeed increases, the flight control electronic control unit reduces the hydraulic pressure available to the PCUs, resulting in less rudder deflection during rudder pedals inputs. If a jam occurs in a rudder power control unit, the corresponding rudder 1 or rudder 2 push-off switch light turns on. The illuminated rudder 1 or rudder 2 switch light must then be pushed to depressurize the affected power control unit. When pressed, the push legend will go out, but the off legend will remain on as a reminder that the switch light has been pushed off. As soon as the power control unit is depressurized, the number 1 rudder hydraulic or number 2 rudder hydraulic caution light will turn on. The flight control electronic control unit will then reschedule the regulated hydraulic pressure to the operative power control unit to maintain the required rudder authority. Rudder trim is accomplished by a rudder trim control knob on the center console. Turning the knob operates an electrical trim actuator which supplies a trim signal to reposition the rudder neutral point of the feel unit, causing the rudder to move left or right. This newly trimmed position is sensed by the pilot as the neutral position. Turning the rudder trim control knob to the left or right first graduation line produces a slower trim rate. Turning the control knob fully to the second graduation produces a faster trim rate. When released, the control knob returns to the neutral position. Rudder trim indication is performed via an integral linear variable differential transformer, LVDT, that monitors the trim actuator position and sends this position to the rudder trim indicator. If the trim signal fails, the trim actuator remains functional, but an off-scale deflection is shown on the rudder trim indicator. Rudder position indication is displayed on the pilot's MFD. Rudder hydraulic system malfunctions are indicated by the following caution lights. The number 1 or number 2 rudder hydraulic caution light illuminates whenever the number 1 or number 2 hydraulic system hydraulic pressure is not available, or the Flight Control Electronic Control Unit, FCECU, has shut down a power control unit, hydraulic actuator, PCU, because of a malfunction, or the rudder number 1 or rudder number 2 push-off switch has been pushed. The rudder control caution light illuminates whenever the Flight Control Electronic Control Unit is unable to control rudder pressure, or number 1 and number 2 hydraulic systems have failed, or airspeed number 1 is not equal to airspeed number 2 plus or minus 17 knots. IAS mismatch message on PFD and elevator feel, spoiler outboard, and pitch trim caution lights will also turn on. Airspeed must be reduced to below 200 knots. The yaw damper is an actuator that supplies automatic compensation for minor yaw oscillations in flight and also improves the directional stability and turn coordination of the aircraft. The yaw damper acts independently or as an autopilot servo in conjunction with the automatic flight control system for rudder deflections to either side of center of maximum 4.5 degrees. The yaw damper can be engaged or disengaged by momentarily pressing the yaw damper push button on the powered flight control surfaces panel. When engaged, pointers on the left and right sides of the yaw damper switch light illuminate. The rudder pedals are adjusted in the lateral plane. The assembly is mounted below the flight compartment. Movement of the pedals around their support tubes, a lever and a push rod on each system transfer the rudder movement to the rudder input quadrant and to the cable system. The mixer quadrant is a 3-pulley quadrant installed below the cabin floor. It combines rudder control from the 2 rudder forward quadrants and transmits it to the rudder aft quadrant. The 2 pairs of control cables are routed aft from the rudder forward quadrants to the upper 2 pulleys of the mixer quadrant. From the lower pulley of the mixer quadrant, a single pair of cables is routed aft and below the left side of the cabin floor. The cables pass through the pressurization seal at the rear pressure dome in the aft fuselage, then up to the rudder aft quadrant in the vertical stabilizer. This dual cable arrangement ensures continued rudder control if a single cable failure occurs between either the pilot or co-pilot's rudder pedals and the mixer quadrant. The rudder aft quadrant is located halfway up the vertical stabilizer next to the power control unit. The rudder aft quadrant transmits rudder control inputs from the mixer quadrant to the power control units. The rudder aft quadrant has the primary travel stops for the rudder cable system. Rotation of the aft quadrant is opposed by 2 feel springs which supply an artificial feel to the rudder pedals. There are two power control units, one located above the other in the vertical stabilizer. The PCUs are attached directly to the midpoint of the fore-rudder section. Movement of the PCUs causes the rudder to move and give directional control and stability to the aircraft. There are two PCU input bungees, one for each rudder PCU. Each PCU input bungee has a spring strut and a motion detector with a limit switch. In the event of a jam of the PCU or its linkage, any further pilot input to the rudder aft quadrant causes an inner spring in the strut to either stretch or compress. This causes the motion detector cam arm to trigger the limit microswitch and the applicable Rudder 1 or Rudder 2 rudder switch light on the glare shield panel to come on. The rudder aft quadrant is mechanically linked to three distinct units: the trim actuator, the rudder feel and summing unit, and the yaw damper. Each unit input has its own effect on the rudder control system. All three units are attached to a summing bar. The bar sums the inputs and then transmits the force as a single input to the rudder power control units, PCUs. The trim actuator is attached to the front of the vertical stabilizer and connected at the rear to two trim arms that form part of the summing unit. The trim actuator has a DC motor that extends and retracts the actuator. The rudder feel and summing unit gives artificial feel to the pilots when operating the rudder pedals. The rudder feel and summing unit is installed in series with the rudder control system and is located behind the rudder aft quadrant. The rudder feel and summing unit has two feel springs attached to a summing bar that is connected to the rudder hydraulic power control units. Rotation of the feel and summing unit from neutral in either direction extends one or the other of the feel springs to give artificial feel during movement of the rudder pedals. The yaw damper is a linear servo actuator. The yaw damper responds to signals from a dedicated accelerometer to supply small rudder deflections to compensate for yaw oscillations in flight. The yaw damper has its own summing arm, which mechanically transmits any yaw damper inputs onto the rudder feel and summing unit. The yaw damper acts independently or as an autopilot servo in conjunction with the automatic flight control system. The rudder is a primary flight control surface that is attached to the rear spar of the vertical stabilizer. The rudder is divided into two sections: the fore-rudder and the trailing rudder. The fore-rudder is attached to the vertical stabilizer at four main hinge points, and the trailing rudder is attached to the fore-rudder rear spar, also at four main hinge points. Each rudder has two safety hinges supplied. One is located above the upper main hinge point, and one is located below the lower main hinge point. In case of main hinges wear, the safety hinges take an increasing share of the load. There are extensions on the right side of the center hinge fittings, which act as attachment points for the rudder power control units. There is a fitting between the upper and center hinge fittings, providing the attachment point for the linear variable digital transducer, LVDT. Pitch control of the aircraft is maintained by two independent mechanically controlled and hydraulically powered elevators. The pilot's control column operates the left elevator, and the co-pilot's column operates the right elevator. The two control columns are normally interconnected by a shaft. Simultaneous movement of both elevators is provided. In the case of a jamming elevator, the two systems can be disconnected. Limited pitch control is then provided by the remaining elevator. Each system consists of the control column, the forward quadrants, and two fully independent cable and pulley control circuits to the elevator power control units. There are three identical hydraulic power control units on each elevator. The outboard and center power control units on each elevator are active at all times, while the inboard power control unit is a standby. The left and right outboard power control units are supplied by the number 1 hydraulic system. The left and right center power control units from the number 2 hydraulic system, and the left and right inboard standby power control units, when required, from the standby number 3 hydraulic system. Pitch commands from the control columns are transferred to the elevator power control units, which move the elevator surfaces. During normal operation with the number 1 and number 2 hydraulic systems in operation, the inboard power control units can be selected by pressing the hydraulic number 3 isolation valve push button on the hydraulic control panel. When pressed, the number 3 isolation valve opens, indicated by the elevator pressure caution light, and activates the inboard power control units. The number 3 isolation valve is automatically activated when number 1 and/or number 2 hydraulic system fails. In the event of a jammed elevator, the left and right systems can be separated by the pitch disconnect system. The system is controlled by a vertically mounted handle on the center console. In normal position, the clutch is engaged. A spring retains the clutch to the clutch plate to connect the pilot's and co-pilot's control columns positively. When the handle is pulled out and rotated 90 degrees, the clutch disengages and disconnects the two control columns. The pilot with the free control column will have pitch control. Artificial pitch feel is provided by pitch feel and trim units. The elevator column force increases with column displacement as a function of airspeed and normal acceleration of the aircraft. As airspeed increases or decreases, the flight control electronic control unit commands the pitch feel actuators to extend or retract respectively. This results in an increase or decrease in the amount of artificial feel acting on the control columns. In case one pitch feel actuator fails, the elevator feel caution light will illuminate and the system will continue to operate by using the operational actuator. Pitch trim is accomplished by two pitch trim actuators that are controlled automatically by the autopilot or manually by the trim switches on the pilot's and co-pilot's control wheels. Pitch trim signals from the trim switches or from the autopilot are prioritized by the flight control electronic control unit in this order: pilot, co-pilot, and autopilot. The flight control electronic control unit also controls the elevator pitch trim rate according to the airspeed of the aircraft. At airspeeds below 150 knots indicated airspeed, the trim actuators operate in high-speed mode. At airspeeds greater than 250 knots indicated airspeed, the trim actuators operate in low-speed mode. Between 150 and 250 knots indicated airspeed, the flight control electronic control unit adjusts the trim rate. Elevator trim control is provided through the actuation of trim switches located on the outboard hand grip of each control hand wheel. The pitch trim switches are divided into two halves. Both halves must be operated for pitch trim commands and are spring-loaded to the center off from nose down and nose up positions. Whenever the Flight Control Electronic Control Unit detects that manual pitch trim command persists for longer than 3 seconds, an RL warning sounds and the elevator trim push-off switch light on the glare shield panel illuminates. The RL warning will stop, and the elevator trim push-off switch light will extinguish when the pitch trim command is removed or the switch light is pressed. Pressing the switch light will deactivate the elevator trim. During flap extension or retraction operations between 15 and 35 degrees, automatic pitch trim is provided to reduce the pitch forces felt on the control column. The flap auto trim activates and deactivates automatically without any enunciations. Nose down pitch trim is commanded when flaps are extended, and nose up pitch trim when the flaps are retracted. Flap auto pitch trim is active when the flaps are selected from 15 to 35 degrees and the autopilot is not engaged. The airspeed is less than 180 knots indicated airspeed, and manual pitch trim is not commanded. Flap auto trim will temporarily disengage if manual pitch trim is applied. The elevator trim position indication is displayed on the pilot's MFD and on the elevator trim indicator located in the center console. The indicator is labeled in U for nose up, in D for nose down, and TO for takeoff. A white band next to each of the takeoff labels shows the takeoff trim range. Whenever the elevator trim set is outside the takeoff range and both power levers are advanced, an RL warning will sound. Whenever a mismatch occurs between the left and right elevator, an elevator asymmetry caution light will illuminate. Pitch control movement of the pilot's and co-pilot's control columns is transferred by push rods to the left and right forward elevator quadrants below the flight compartment floor. Tension regulator springs installed in each of the forward quadrants give correct tension of the elevator control cables according to ambient temperature. The stick pusher quadrant is directly attached to the left forward quadrant with input from the stick pusher actuator. From the forward elevator quadrants, the elevator cables are routed aft below the flight compartment and cabin floor through the rear fuselage and upwards to terminate at the two aft, left and right, elevator quadrants in the vertical stabilizer. The aft quadrants transfer the pitch control movement through push rods and bell cranks to the PCU input torque tubes. The left-aft pilot's elevator quadrant also has input from the Automatic Flight Control System, AFCS. The torque tubes then transfer the pitch control movement through the PCU input bungees to the elevator PCUs, which are attached to the elevator control surfaces. Extension or retraction of the PCUs moves the elevator surfaces according to the pitch commands from the pilot or the autopilot. The elevator control system has 6 identical elevator PCUs, 3 attached to each elevator surface and the horizontal stabilizer rear spar. Each elevator PCU is a hydromechanical servo actuator which receives pilot input commands from the PCU input bungees and the PCU input torque tubes. An elevator PCU compensator maintains fluid within both inboard PCUs to give gust damping on the ground. It compensates for a change in fluid volume that occurs due to thermal expansion and contraction. The compensator is installed in the return line of the number 3 hydraulic system and locks hydraulic pressure in the number 3 elevator PCU. This prevents structural damage to the elevator surfaces during windy conditions. The Linear Variable Differential Transformer, LVDT, is a single-channel, single-sensor LVDT. It senses the elevator surface position and transmits the position data to the Flight Control Electronic Control Unit, FCECU, and to the Powered Flight Control Surface Indicator, PFCSI, on the pilot's MFD. There are 2 LVDTs located in the horizontal stabilizer, one attached to each elevator surface. The dual-pitch feel and trim unit is in parallel with the pitch control linkages located near the elevator aft quadrants in the vertical stabilizer. Each pitch feel and trim unit has a feel actuator which positions a spring to produce the desired amount of feel at the control column. Each pitch feel actuator is a single electromechanical unit which has one DC motor. The left motor controller receives its commands from the FCECU channel 1, and the right motor controller receives its commands from the FCECU channel 2. A pitch trim actuator is installed on top of each pitch trim unit and gives elevator trim. The pitch trim actuators are installed in an electromechanical unit that includes 2 DC motors that are installed in line so that only one motor is needed at any time to operate the 2 actuators. Pitch trim is accomplished by 2 pitch trim actuators that are controlled automatically by the autopilot or manually by the trim switches on the pilot's and co-pilot's control wheels. Pitch trim signals from the trim switches or from the autopilot are prioritized by the Flight Control Electronic Control Unit in this order: pilot, co-pilot, and autopilot. The Flight Control Electronic Control Unit also controls the elevator pitch trim rate according to the airspeed of the aircraft. At airspeeds below 150 knots indicated airspeed, the trim actuators operate in high-speed mode. At airspeeds greater than 250 knots indicated airspeed, the trim actuators operate in low-speed mode. Between 150 and 250 knots indicated airspeed, the Flight Control Electronic Control Unit adjusts the trim rate. Each pitch feel and trim unit has a feel actuator which positions a spring to produce the desired amount of feel at the control column. The stall protection system indicates that the aircraft is nearing a stall condition. When the aircraft is in a stall condition, it gives a positive input to help the flight crew regain control. The stall protection system has 2 primary functions: the stick shaker and the stick pusher function. The stick shakers give a tactile and aural warning of a near stall condition, while the stick pusher is used when the aircraft is in a stall condition to move the elevators, reducing the wing angle of attack. The stall protection system operation mode is divided into the pre-flight mode and the in-flight mode. In the pre-flight mode, the stall warning system can be tested by selecting the stall warning toggle switch located on the pilot side console. In the in-flight operational mode, the stall protection system operates when the airspeed and above ground altitude are near their lower limits. The stall protection system, controlled and operated by the stall protection modules number 1 and number 2, use the following parameters to calculate when the aircraft is near a stall condition. Angle of attack data. Flap position. Mach number. Engine torque. And icing status. To calculate the stick pusher operating angle, the following parameters are used by the stall protection modules. Angle of attack, flap position, Mach number, power lever angle, condition lever angle, and icing status. The stall protection modules calculate when to start and when to cancel the stick shaker and stick pusher operations. When the stall protection modules operate their related stick shaker, a signal is sent to the automatic flight control system to disengage the autopilot and to the ground proximity warning system to prevent the pull-up audible alerts. For the stick pusher calculations, each stall protection module uses the average value of the two angle of attack inputs. When the aircraft is near a stall condition, the stall protection system's stick shakers cause the control columns to vibrate. In addition to this tactile warning, the stick shaker motor and the rattling of the mechanism on the control column creates a loud noise. When only one stick shaker is operating, its vibration is transmitted through the torque tubes and the push-pull rod to the other control column. The stick pusher will move the control columns to decrease the angle of attack of the aircraft as soon as the aircraft is in a stall condition. The pilots can override the stick pusher clutch by applying an opposite breakout of 36 kilogram force, 80 pound force, to the control column. After breakout, 30 kilograms force or 66 pound force is needed to continue to override the clutch. However, the stick pusher shut-off switch light can be pressed to turn off the stick pusher. If one stick pusher shut-off switch light is pushed and latched, the off caption will illuminate on both annunciator switch lights and the stick pusher actuator will be shut off. To release the pusher, both switch lights must be deselected and the off captions in the two switch lights will extinguish. Malfunctions of the stall protection system are shown with caution lights. The number 1 stall system fail and number 2 stall system fail caution lights come on immediately in flight when malfunctions that prevent stick shaker and stick pusher operations are sensed. Malfunctions of non-critical parameters or stick shaker motors malfunction are not shown in flight but 30 seconds after the aircraft has landed. A stall warning test should be conducted daily. To perform the test, the stall warning toggle switch is set to test 1. And then to the test 2 position. The switch must be held in the appropriate position for more than 10 seconds. The left and right independent elevator surfaces are attached to the horizontal stabilizer by 4 hinges using low-torque plain roller bearings. There's an inboard and an outboard hinge fitting and 2 more hinge fittings near the center of the control surface front spar. The 3 PCU attachment fittings are located near the center hinge points. Each elevator has a span of 174 inches, 4.42 meters. The elevator surface travel is 30 degrees up and 20 degrees down. Flutter suppression is given by a retained stiffness in the PCUs. The left and right elevator control circuits are connected to each other by a torque tube installed below the flight compartment floor. The torque tube connects the 2 control columns through a clutch mechanism. The pitch disconnect system has a vertically mounted pitch disc handle located on the left side of the center console. This handle is connected to the clutch mechanism by a cable routed below the flight compartment floor. If a jam occurs in either control circuit, the pitch disc handle in the flight compartment is pulled to disconnect the left elevator circuit from the right elevator circuit. Pulling the pitch disc handle draws back the clutch lever and cam assembly. The turning cam pulls the clutch from the clutch plate. The two columns are now separated and move independently. Turning the handle 90 degrees locks it in this position. Turning the handle back 90 degrees and releasing the handle allows the springs to force the clutch to clutch plate. The clutch re-engages if the columns are aligned. The wing flap system consists of a drive system, a control system, and 4 flap sections. The inboard flap is located between the fuselage and the nacelle. The outboard flap is located between the nacelle and the aileron. A flap selection of 0, 5, 10, 15, and 35 degrees is provided. The flap position can be seen on the flap position indicator on the co-pilot's MFD. The flap control system is operated by the flap selector. The détente cam provides settings from 0 degrees in the full forward position via 5, 10, and 15 degrees to 35 degrees in the full aft position. To change the flap setting, the trigger must be pulled to lift the cam follower. At the next position, the trigger must be released. The cam follower will engage in this position. The flap drive system consists of the flap power unit, the transmission system, and 4 ball screw actuators in each wing. The flaps, which are connected to ball screw actuators, are operated by a primary drive shaft. The flap power unit, operated by number 1 hydraulic system and actuated by the flap selector, moves the flaps to their selected positions. If during flap extension or retraction a flap failure occurs, either the flap power or the flap drive caution light will come on. If the flap power caution light comes on, a flap failure has occurred. The flaps will lock in the last position reached prior to failure. All further flap movements will be inhibited. If the flap drive caution light turns on, this is a flap fault indication. The flaps may still be operable in some instances with reduced performance. The fault is automatically reset if the condition goes away. The landing flap selector switch on the hydraulic control panel is turned to one of 3 landing flap settings for the insufficient terrain clearance mode. When the aircraft flap select lever is set at other than the landing flap selector switch setting, a "too low flaps" aural alert will sound when the above ground level altitude becomes less than 170 feet. When the flap selector lever is in the 0 degrees position, all flaps are retracted, and the flap position indicator points to 0 degrees. Moving the flap selector lever, a signal is sent to the flap control unit to indicate that the flap lever is in a new position. The flap control unit starts the actuation when the flap lever reaches the first gate, and an arming switch located on the flap selector lever is activated. When the flap control unit receives the enabling signal, It commands the flap power unit to start moving the flaps to the newly selected position. When the selected flap position has been reached, the flap control unit stops any further flap movement. The flap control unit, FCU, is a microprocessor-based controller located below the cabin floor. The FCU performs the following functions: processes the signals from the flap position and flap lever transducers to monitor the actual flap position and control the flap movement to the new position. Receives a pressure on-off signal from the pressure switch in the flap power unit. Receives the enabling signal from the arming switch on the flap lever transducer. Performs internal checks to monitor the FCU for faults, built-in test. Receives the weight on wheels signal to inhibit the power to the built-in test mode during flight. Performs asymmetry and non-selected flap movement monitoring. Supplies the on-off power signal to the flap power unit solenoid valve. Supplies controlled current to the FPU electro-hydraulic solenoid valve to actuate the system. Supplies the flap power and flap drive signals to the aircraft indicating and monitoring system. Supplies the flap selected position to the indication and monitoring system. Supplies system status information through the RINC 429 link and the RS422 serial port. The flap selector lever mechanically operates the flap lever transducer, which sends the flap position demand signal to the FCU. The arming switch is located on the flap selector lever. The arming switch circuit senses the position of the flap selector lever. If the lever is in one of the 5 detente positions, the arming switch sends an enabling signal to the FCU, which lets the flaps move to the selected position. The flap selector lever is mechanically connected to the rudder restrictor mechanism, which restricts the rudder to half travel whenever the flaps have been selected to the 0-degree position. The flap power unit, FPU, is located on the wing aft spar to the right of the aircraft centerline. The FPU converts aircraft hydraulic power to rotary mechanical power to operate the flap actuators, raising or lowering the flaps as selected. Hydraulic pressure is supplied from the number 1 hydraulic system to the FPU. A return line carries the hydraulic fluid back to the system reservoir. There are 2 torsion bars installed on the aircraft's center wing rear spar. The 2 shafts transfer the rotary movement of the FPU to the transmission shafts and actuators on the wings. The transmission shaft system transmits the mechanical power from the flap power unit to the 8 flap actuators. The transmission shafts are located along the aft spars of the wings to engage with each of the flap actuators on the left and right wings. The flap actuators are mechanical units designed to convert high-speed, low-torque rotary drive to a low-speed, high-torque linear drive. The flap actuators move the flap surfaces to a selected position and keep the selected position against the aerodynamic forces on the flap surfaces. The flap actuators receive the mechanical input from the transmission shafts and the torsion bars. The number 1 and number 2 flap actuators on each wing operate the inboard flap section, and the number 3 and number 4 flap actuators on each wing operate the outboard flap section. The no-back torque limiter device on each flap actuator keeps the flaps in the selected position regardless of the aerodynamic loads. Maximum flap travel is limited by the use of non-jamming end stops. If a flap failure occurs, either the flap power or the flap drive caution light comes on. The flap tracks control the incidence angle of the flaps during flap deployment. There are 5 flap tracks on each wing, which support the inboard and outboard flap section. The inboard and outboard flaps are installed with rollers at each end, which engage in tracks. The rollers give support for the flap and allow for smooth extension and retraction. Deadweight rollers are used for support when the aircraft is on the ground. The Flap Position Indication System has a Flap Position Indication Unit, FPIU, located below the cabin floor. It also has 2 flap position transducers located on the outboard flaps. The Flap Position Indication System has 2 functions. Supplies indication of the current flap position to the co-pilot's multifunction display indicator, and monitors the position of the flaps during flap deployment, sending the position data to the Flap Control Unit, FCU. There are 2 large flap sections on each wing. The inboard flap is supported at each end by 2 hidden tracks, one on the fuselage and the other on the inboard side of the engine nacelle. The outboard flap is supported by 3 tracks, one on the outboard side of the engine nacelle and 2 at intermediate stations below the wing. Each flap is a single slotted high-lift Fowler action type flap. The roll spoilers augment the ailerons in providing lateral control. They are installed on the upper surface of the wing forward of the outboard flaps. The spoilers extend 75 degrees upward when fully deflected. The system is hydraulically operated by the number 1 system for the inboard spoilers and the number 2 system for the outboard spoilers. The spoilers rise in parallel with the upgoing aileron. At speeds above 170 knots, only the inboard spoilers operate. There are 3 modes of spoiler operation: flight mode, ground mode, and the taxi. In flight mode, with airspeeds greater than 170 knots indicated airspeed, only the inboard spoilers operate. The Flight Control Electronic Control Unit disables the outboard spoiler. If the outboard spoilers are not disabled above 185 knots indicated airspeed or activated below 150 knots indicated airspeed, the spoiler outboard caution light illuminates. Pushing either spoiler 1 or spoiler 2 switch light inhibits hydraulic pressure to its related spoiler power control unit extend port. This turns on the roll spoiler inboard hydraulic or roll spoiler outboard hydraulic caution light. The continuous hold-down pressure returns the related spoilers to the retract position. For ground mode operation, there are 2 lift dump valves in the inboard spoiler system and 2 in the outboard spoiler system for ground spoiler operations. The lift dump valves in each spoiler system are hydraulically in series, meaning that both valves must open together before the spoilers can extend on the ground. The lift dump valves are energized by signals from the Flight Control Electronic Control Unit and the Proximity Sensor Electronic Unit when the following conditions are met. The flight taxi switch is in the flight position. The power levers number 1 and 2 are positioned to less than flight idle plus 12 degrees. And the weight on wheels proximity on both landing gear detect the aircraft has landed. As soon as Flight Control Electronic Control Unit and the proximity sensor electronic unit receive these input signals, the lift dump valves are energized open, and hydraulic input commands are sent to the power control units to fully extend both inboard and outboard spoilers. When all spoilers are deployed, the roll inboard and roll outboard advisory lights illuminate. If a lift dump valve fails to energize, its inboard or outboard spoilers will not extend in ground mode. The applicable roll spoiler inboard ground or roll spoiler outboard ground caution light will come on after a time delay of 5 seconds. After the aircraft has landed, all spoilers will extend automatically. The spoilers can be retracted for taxiing by selecting the flight taxi switch to taxi position. The flight taxi switch has 2 positions, flight and taxi. The switch is spring-loaded to the flight position, but must be manually selected to the taxi position and is maintained in this taxi position by a hold-in solenoid. However, if both power levers are advanced above flight idle plus 12 degrees for another takeoff, the flight taxi switch automatically moves to flight position. All spoiler panels retract, and the roll inboard and roll outboard advisory lights will extinguish. In case of a non-indicated jam in the roll control system, the roll disconnect handle must be pulled in order to separate aileron and spoilers. This closes the roll spoiler disconnect jam switches. If the roll spoiler system is now found to be jammed, a large aileron deflection is necessary to correct a roll. The aileron quadrant switch will close at 50 degrees in either direction to illuminate both powered flight control shutoff switches. In this situation, a spoiler has remained extended. By depressing both powered flight control shutoff switches, both systems are immediately depressurized. The jammed-up spoiler will be retracted by the hold-down pressure. The spoilers are controlled from the pilot's control column. Rotary movement of the pilot's control wheel is transmitted by a chain and sprocket mechanism to a lever on the base of the column. The lever is connected to the spoiler quadrant via a push rod. The quadrant integrates a tension regulator. The tension of the roll spoiler cable to the splitter quadrant is maintained constantly under all temperature conditions by the tension regulator. From the splitter quadrant, the mechanical movement continues via cables, push rods, levers, and quadrants to the spoiler power control units. The clutch units, one in each wing, are installed centrally below the 2 spoiler panels. The units contain clutch mechanisms to allow for a jam in the controls for either spoiler panel, while keeping control over the remaining spoiler system. In case one spoiler system jams, the clutch plate will be depressed against the springs to disengage and isolate the affected spoiler so the remaining system can work normally. The depressed plate will actuate a micro switch which will illuminate the roll spoiler's push-off switch light. Pressing the switch removes pressure from the appropriate system. The second spoiler has the same system installed on the underside of the spoiler clutch. The power control units, PCUs, located at the wing rear spar, transfer mechanical input commands into hydraulic inputs. The input lever operates a servo valve which directs hydraulic pressure to the actuator piston. A command input moves the actuator rod with an attached feedback linkage. Actuator travel stops when the actuator rod position corresponds to the input lever position. The outboard spoiler PCU is powered by the number 2 hydraulic system. Number 1 system powers the inboard spoiler PCU. The number 1 unload valve located on the left wing root area controls both inboard spoiler PCUs. And the number 2 unload valve located on the right side wing root area controls both outboard spoiler PCUs. In flight mode, the number 2 unload valve is operated electrically through the Flight Control Electronic Control Unit to prevent extension of the outboard spoilers when aircraft airspeed is above 170 knots. The number 2 unload valve can also be operated by depressing the roll spoiler switch light SPLR2 push off. If the inboard spoiler PCU linkage jams, the number 1 unload valve will prevent extension of the inboard spoilers when the SPLR1 push-off switch light is pushed. The LVDT gives position indication through the FC ECU to the Powered Flight Control's Surface Indicator, PFCSI, in the flight compartment and to the Flight Data Recorder. The LVDT is attached to a bracket on the aft face of the wing rear spar and a bracket on the spoiler panel. The 2 lift dump valves for the inboard, number 1 spoiler system, are located on the left side of the aircraft in the wing to fuselage attachment area. The 2 lift dump valves for the outboard, number 2 spoiler system, are located on the right side of the aircraft, also in the wing to fuselage attachment area. The 2 valves in each system are connected hydraulically in series. Both valves must open to let pressure through to the related spoiler PCU. This reduces the possibility of in-flight symmetric deployment. After landing, with the aircraft weight on wheels signal and both power levers set below flight idle plus 12 degrees, all lift dump solenoid valves are energized. This supplies hydraulic pressure to the extend side of both spoiler actuators, extending all spoiler panels symmetrically. Four spoiler panels are installed on the upper surface of the wing forward of the outboard flaps. The panels are identified as inboard and outboard and are operated hydromechanically using control wheel inputs in conjunction with the ailerons. Each of the spoilers is attached by 3 hinge fittings on the aft face of the rear wing spar. The power control units attached to the inboard panels are supplied with hydraulic pressure from number 1 hydraulic system. The PCUs attached to the outboard panels are supplied by number 2 hydraulic system. The aileron control system is a mechanically operated system. Gust protection for the ailerons is supplied by a gust lock mechanism operated from the flight compartment. The aileron gust lock system locks the ailerons in a neutral position when the aircraft is parked or being taxied. This protects the aileron surfaces from damage due to strong gusts. The aileron gust lock mechanism is located on the aft face of the wing rear spar, right of the aircraft center line. The mechanism has a cable-operated gust lock lever, a spring-loaded plunger, 2 tension springs, and a lock plate on the aileron splitter quadrant. When the control lock lever release is pulled up and the lever is moved from the off to the on position, the gust lock lever is pivoted by the cable to the locked position. If the ailerons are moved to the neutral position, the plunger engages in the lock plate slot and prevents the aileron splitter quadrant from rotating. This locks the ailerons in the neutral position. two tension springs pull the gust lock lever towards the off position. This gives positive disengagement of the gust lock mechanism and unlocks the ailerons if a cable fails.